Hi, my name is Chad, and my part in this project is designing the power system of the electric skateboard. The goal for improvement of the power system is to increase the overall top speed of the electric skateboard. The motivation to accomplish this is to increase the speed of the skateboard. So far, I am working on a way to implement a new component that will increase the skateboard's top speed. Currently, the power system can be represented by the following block diagram as shown on the screen. The voltage for the system is provided by a battery or battery bank, which is just two or more batteries that are connected in series. The battery bank supplies DC voltage to a motor controller. The primary purpose of the motor controller is to transform the DC voltage supplied by the battery to AC voltage to a motor. The current motor control is fan-cooled, which means that there is a DC output voltage line that is connected to the microcontroller board. The current motor is rated as 190 kilovolts, which means that it provides 190 RPMs for every volt provided to the motor. So to accomplish an increase in top speed, an increase in voltage supplied to the motor is the best answer. With the original setup, the bottleneck for supplied voltage is the motor control, which is only rated to handle a 6S battery input. The batteries that are being used are Li-Pro batteries, which generally provide about 4 volts per cell. With the 6S setup, we are limited to a 24 volt output. Our plan is to replace the current motor control with a motor control that can handle up to 12S, making the bottleneck the current motor, which is rated to handle 10S. Ideally then, we should be able to deliver about 40 volts to the motor, allowing for a max RPM of 7,600 compared to the current 4,560 RPM. This increases the ideal rated top speed by 166%. From experience, the top speed is around 22 miles an hour, so ideally the new top speed may reach 36 miles per hour, theoretically speaking, but it should reach at least 32 miles an hour with the increasing RPMs. We recently received the motor control and are working on implementing it into the system. While the motor control can handle a 12S input, it does have some differences that present some new challenges. As the current motor control is a fan-cooled, the planned implemented motor control is cooled with a heat sink. This heat sink requires no additional power, so there is no DC output from the new motor controller. Because of that, we have to find a way to power the microcontroller, alternatively. The current plan is to create a voltage divider circuit that will have the board in parallel with a resistor that is in series with another resistor, stepping down the voltage in a safe input value for the microcontroller board. Although the board is rated for 22 volts, it is better to ensure that there is not too much voltage or current passing through the microcontroller board. We have built a base design from taking measurements of voltage drops across a parallel resistor in series with a resistor. In April, we are going to mill a circuit board that will be the voltage divider of the system. Another issue that needs to be resolved with the implementation of a new motor control is the lack of an overall power switch. The current motor controller has a switch included, but the new one does not. Because the current going through the system is relatively high, and most switches that have been researched are rated for less than 3 amps, we have to develop another circuit that would allow for a single power switch that can control the whole system. We plan to start developing the circuit once we have the voltage divider working.